February 16th, 1944. Freya radar station, northeast of Berlin. Gefreiter Klaus Hoffmann pressed his headphones tighter against his ears as the cathode ray tube before him painted an impossible picture. The green phosphor dots marching across his screen represented a formation so massive it seemed to defy the physical limitations of air warfare itself. He counted the returns methodically, his training overriding the disbelief building in his chest. 20 aircraft. 40. 60. The numbers kept climbing. By the time the formation crossed into effective tracking range, Hoffmann had identified over 200 individual radar returns, each one representing a 4-engine bomber carrying thousands of pounds of high-explosive ordnance toward the heart of the Reich. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Freya system's antenna array, stretching over 8 meters wide, rotated slowly on its concrete foundation, continuously sweeping the sky for enemy aircraft. Operating at a wavelength of approximately 2.4 meters, the radar could detect formations at ranges exceeding 120 kilometers. What made this particular morning different wasn't the presence of American bombers. By February 1944, daylight raids had become grimly routine. What shocked Hoffmann was the altitude reading displayed on his oscilloscope. The formation was flying at 9,000 meters, approximately 30,000 feet above sea level. This altitude placed them well above the effective ceiling of most German anti-aircraft batteries. The standard Flak 38, the backbone of German air defense, could theoretically reach altitudes approaching 10,000 meters, but theoretically and effectively existed in different universes. At extreme altitude, shell trajectories became unpredictable. Air density affected fuse timing. Freezing temperatures caused mechanical failures in fire control systems. Most critically, at 9,000 meters, the bombers had entered a realm where oxygen deprivation turned gun crews sluggish, where cold made fingers fumble with loading mechanisms, where simple calculations became mentally exhausting. The Americans had solved this problem through brute force engineering. Their bombers were pressurized, maintaining sea-level atmospheric conditions inside sealed compartments, even at extreme altitude. German intelligence had confirmed this capability through examination of captured aircraft and interrogation of downed aircrews. But understanding a technological capability intellectually and witnessing its operational implications were entirely different experiences. Hoffmann reached for the telephone, connecting his station to the Regional Air Defense Coordination Center at Doberitz. Before he could speak, the watch officer's voice crackled through the line. "We see them, Hoffmann. Vector 225, altitude 9,000 meters, speed approximately 300 kilometers per hour. Confirm?" "Confirmed, Herr Leutnant. Formation strength now estimated at 200-plus aircraft. All returns consistent with 4-engine heavy bombers." There was a pause on the line. When the officer spoke again, his voice carried a weight that Hoffmann recognized. It was the sound of a man calculating odds and finding no favorable outcome. Fighters are scrambling from Jüterbog and Werneuchen. Continue tracking and report any course changes. The Würzburg radar operators at the nearby fire control stations would be frantically calculating firing solutions, feeding data to the flak batteries spread throughout the Berlin defense perimeter. But everyone involved in the air defense network understood the mathematics of high-altitude bombardment. At 9,000 meters, the bombers occupied an operational envelope where German defenses struggled to function effectively. The journey to this moment of technological desperation had begun years earlier, when German engineers first recognized the implications of American industrial mobilization. In 1940, when Boeing submitted its design for what would become the B-17 Flying Fortress, German intelligence analysts studying photographs and technical specifications noted several characteristics that seemed to contradict conventional bomber design philosophy. The aircraft featured 4 Wright Cyclone radial engines, each producing 1,200 horsepower. This massive power plant drove turbo superchargers that maintained engine performance at high altitude. The superchargers used exhaust gas energy to compress incoming air, compensating for the thin atmosphere at extreme altitude. German bombers used mechanical superchargers that drew power directly from the engine, reducing available thrust. The American exhaust-driven turbo supercharger represented a more sophisticated engineering solution. More significantly, the B-17 incorporated a pressurized crew compartment. This was not merely a comfort feature. At altitudes exceeding 7,000 meters, human physiology became a limiting factor in combat effectiveness. Without supplemental oxygen, crews suffered hypoxia within minutes. Even with oxygen masks, the extreme cold at altitude created severe operational challenges. Temperatures at 9,000 meters routinely dropped to -40 degrees Celsius. Exposed skin froze within seconds. Metal became brittle. Hydraulic fluid thickened. The B-17's pressurization system maintained an internal atmosphere equivalent to approximately 2,400 meters altitude, even when flying at 9,000 meters. This allowed crews to function normally without oxygen masks for extended periods. They could concentrate on navigation, bombardment, and defensive gunnery without the physical stress of operating in an environment hostile to human life. German bomber design philosophy had evolved along different paths. The Heinkel He 111, the Junkers Ju 88, and the Dornier Do 17 all emphasized speed and maneuverability over altitude performance. These aircraft could reach altitudes of 7,000 meters, but operated most effectively between 3,000 and 5,000 meters. This altitude range placed them well within reach of enemy fighters and anti-aircraft fire. The strategic rationale behind German bomber design reflected operational doctrine developed during the Spanish Civil War and the early campaigns of World War II. German theorists, particularly Oberst Walther Wever, had advocated for strategic heavy bombers capable of deep penetration missions. Wever's death in an aircraft accident in 1936 removed the primary advocate for four-engine heavy bomber development from German planning circles. His successors, particularly Ernst Ude and Hans Jeschonek, emphasized close air support and medium bomber capabilities. They argued that future warfare would require tactical flexibility and rapid response rather than strategic bombing campaigns. Germany would win wars through lightning campaigns, supported by medium bombers working in coordination with ground forces. Heavy strategic bombers represented an inefficient allocation of limited industrial resources. This decision made perfect sense based on Germany's early war experiences. The campaigns in Poland, France, and the Low Countries validated the tactical approach. Medium bombers, supported by fighters, delivered devastating attacks on enemy formations and infrastructure. The Luftwaffe achieved air superiority through aggressive fighter operations and tactical bombing that disrupted enemy command structures. But the Battle of Britain exposed the limitations of this doctrine. German medium bombers attempting to attack British cities in daylight suffered catastrophic losses to RAF fighters. The Heinkel and Dornier bombers, designed for tactical operations at medium altitude, proved vulnerable to determined fighter opposition. Lacking sufficient defensive armament and unable to climb above fighter intercept altitude, they required extensive fighter escort that stretched German fighter resources beyond sustainable levels. The Luftwaffe attempted to solve this problem by switching to night bombing operations. Under cover of darkness, bomber formations could evade fighter interception and deliver attacks against British cities and industrial targets. But night bombing presented its own challenges. Navigation became extremely difficult. Target identification was nearly impossible. Bomb accuracy dropped dramatically. By 1941, British defences had evolved to counter night bombing through development of ground-controlled intercept radar systems and specialised night fighters equipped with airborne radar. German bomber losses in night operations began climbing toward unsustainable levels. The strategic bombing campaign against Britain achieved significant destruction, but failed to break British industrial capacity or civilian morale. Meanwhile, across the Atlantic Ocean, American aircraft designers were developing bombers specifically optimized for a different operational concept: high-altitude precision daylight bombing. The Boeing B-17 Flying Fortress and the consolidated B-24 Liberator both incorporated the technological capabilities necessary to execute this doctrine: turbo superchargers for high-altitude performance, pressurized crew compartments for extended operations above 7,000 meters, heavy defensive armament, typically 12 or 1350 caliber machine guns, providing overlapping fields of fire against fighter attack, and most critically, the Norden bomb sight, a sophisticated analog computer that calculated bombing solutions, accounting for altitude, airspeed, wind drift, and target motion. Klaus Hoffmann had studied intelligence briefings describing these capabilities. Every radar operator in the German air defense network received regular updates on enemy aircraft performance characteristics. But receiving briefings and witnessing operational reality remained vastly different experiences. The formation crossing his radar screen represented the full operational deployment of American strategic bombing doctrine. 200 B-17 bombers, each carrying approximately 2,000 kilograms of high explosive and incendiary ordnance. Total payload, 400,000 kilograms. 400 metric tons of explosives about to fall on German territory from an altitude where defensive countermeasures struggled to function effectively. The telephone rang again. "Hoffmann, this is Hauptmann Richter at Doberitz. I'm putting you on the command circuit. Continue your narration for the fighter. Controllers." Hoffmann acknowledged and adjusted his headset. Now his observations would be broadcast simultaneously to multiple fighter control stations and anti-aircraft command posts throughout the Berlin defense zone. This was standard procedure for major raids. Coordinated defense required real-time information sharing across all elements of the air defense network. Formation maintaining course 225, altitude 9,000 meters, speed 300 kilometers per hour. Estimated target Berlin city center or industrial districts. Current position approximately 90 kilometers northwest of city limits. Time to target approximately 18 minutes at current speed. Through his headphones, Hoffmann heard the controlled chaos of fighter direction in progress. Controllers at Doberitz were vectoring Messerschmitt Bf 109 fighters from multiple airfields toward intercept positions. But the calculations were brutally unforgiving. The Bf 109G, the model, the primary German fighter in service by 1944, had a service ceiling of approximately 12,000 meters. This gave adequate altitude margin for attacking bombers at 9,000 meters, but climbing to intercept altitude consumed fuel rapidly. The supercharged Daimler-Benz DB 605 engine delivered maximum power only with proper mixture settings and optimal climbing speed. Pilots rushing to intercept might climb too steeply, wasting fuel and reducing effective combat time at altitude, or they might climb too gradually, arriving after the bombers had already released their payload and begun their return flight. The second challenge was armament. The Bf 109 carried relatively light weapons by 1944 standards. Most variants mounted a single 20mm MG 151 cannon firing through the propeller hub, supplemented by two 13mm MG 131 machine guns mounted in the engine, cowling. Some variants carried additional 20mm cannons in underwing gun pods. These weapons were adequate for destroying unarmored targets. A single 20mm high-explosive shell, detonating against an aircraft's wing spar or fuel tank, would cause catastrophic structural failure. But the B-17 was not an unarmored target. American engineers had installed armor plating behind pilot seats, around engine nacelles, and protecting critical systems. The aircraft's aluminum skin, while not armored, was thick enough to resist 13mm machine gun fire at all but point-blank range. Pilots reported that attacking a B-17 formation required closing to within 300 meters to guarantee effective hits. At 300 meters range, the bomber's defensive gunners could bring devastating return fire on attacking fighters. German fighter tactics had evolved throughout 1943 to address these challenges. Head-on attacks from 12 o'clock high became preferred, approaching from directly ahead and slightly above the formation. This attack angle exposed the fighter to fire from only the bomber's forward-firing guns, typically two .50 caliber machine guns in the nose or chin turret. After completing the attack pass, the fighter would dive away, using superior speed to escape before the bomber's dorsal, ventral, and tail gunners could track and engage. But head-on attacks required nerves of steel and perfect timing. The closure rate between attacking fighter and target bomber exceeded 700 kilometers per hour. Pilots had perhaps 2 seconds of firing time before breaking away to avoid collision. Missing the target meant wasting ammunition and fuel with no damage inflicted. The mathematics of intercepting high-altitude bomber formations became increasingly desperate as German fighter losses mounted throughout 1943. Each successful interception cost pilots and aircraft that could not be easily replaced. The Luftwaffe's training pipeline, which had produced exceptionally skilled pilots before the war, now struggled to maintain quality while dramatically increasing quantity. Before 1943, German fighter pilot training required approximately 250 flight hours before operational deployment. Pilots mastered aerobatics, gunnery, tactical formations, and combat maneuvers through extensive practice. By 1944, training hours had dropped below 150. Some replacement pilots arrived at frontline units with as few as 100 total flight hours. These inexperienced pilots faced American bomber crews, who often had 300 to 500 hours of training, including extensive formation flying practice, high-altitude operations, and coordinated defensive gunnery drills. The skill differential showed immediately in combat results. Experienced German pilots could still inflict significant losses on bomber formations, but experienced pilots were dying faster than they could be replaced. Hoffmann watched his radar scope as the massive formation continued its inexorable approach toward Berlin. The Freya system's maximum effective range of 120 kilometers meant he could track the formation for approximately 25 minutes before it reached the city limits. During that time, the air defense network would orchestrate the most sophisticated defensive effort yet developed in military history. Fighter controllers would vector interceptors to optimal attack positions. Flak batteries would calculate firing solutions accounting for altitude, wind drift, and formation speed. Searchlight crews would attempt to illuminate targets for night fighters if the raid extended into darkness. Communications officers would coordinate evacuation of civilians from likely target areas based on the formation's approach vector. All of this coordination depended on accurate radar tracking. The Freya provided early warning and general location information, but for precise tracking necessary for fighter direction and anti-aircraft fire control, the Germans relied on the Würzburg radar system. The Würzburg used a 3-meter parabolic dish antenna that could be precisely aimed at individual targets. Operating at approximately 53 centimeters wavelength, it provided much higher resolution than the Freya's 2.4-meter wavelength. The Würzburg's conical scanning system allowed operators to track targets with accuracy, approaching 0.2 degrees in azimuth and 0.3 degrees in elevation. This precision made the Würzburg ideal for directing both fighters and anti-aircraft guns. A skilled operator could track a single bomber continuously, providing updated position information every few seconds. Flak batteries received this data through telephone lines or radio links, feeding it into mechanical computers that calculated firing solutions. But the Würzburg had critical limitations. Its narrow beam width meant operators needed approximate target locations before they could acquire specific aircraft. This required initial detection by Freya radars, which handed off targets to Würzburg operators once formations came within range. The system worked efficiently when tracking small numbers of targets. Against formations of 200 bombers, it became overwhelmed. Each Würzburg could track only one target at a time. Tracking 200 bombers required 200 Würzburg radars operating simultaneously. Germany had deployed approximately 4,000 Würzburg systems by 1944, but they were distributed across occupied Europe, defending hundreds of potential targets. The Berlin defense zone had perhaps 50 Würzburg radars available on any given day, accounting for maintenance and battle damage. 50 radars tracking 200 targets meant that most bombers would fly to their targets without dedicated tracking. Flak batteries would fire barrage patterns, filling volumes of airspace with explosive shells and hoping for random hits. This was inefficient and wasteful, consuming ammunition while achieving minimal results. But no alternative existed given the technological limitations. Hoffmann heard fighter controllers reporting first contact. Adler, we have visual contact with the formation. Altitude 9,000 meters, heading 225, beginning attack approach from 1 to 0 o'clock high. The tactical radio circuit crackled with terse reports as Messerschmitt pilots maneuvered for attack positions. The bombers maintained tight formation, each aircraft positioned to provide overlapping defensive fire coverage. American doctrine emphasized formation integrity above all else. A bomber that fell out of formation, whether due to battle damage or mechanical failure, became an easy target for prowling German fighters. Staying in formation meant enduring the terror of anti-aircraft fire and fighter attacks while maintaining precise spacing and altitude. This required extraordinary discipline from American crews. The lead bombardier controlled the entire formation's bomb release. All other bombardiers watched the lead aircraft and released their bombs simultaneously when they saw the lead plane's bomb bay doors open. This technique, called formation bombing, concentrated hundreds of bombs into a relatively small impact area, overwhelming target defenses through saturation rather than individual precision. The first fighter attacks began 12 minutes after Hoffmann's initial detection. Through his headphones, he heard the staccato reports. Engaging now. Good hits on number 3 aircraft. Left wing smoking. Breaking away. Taking fire from dorsals. Koenig is hit. Koenig is going down. Each fighter attack lasted seconds. Pilots closed at combined speeds exceeding 700 kilometers per hour. Fired short bursts from their cannon, machine guns, then dove away before the concentrated defensive fire could track them. Successful attacks damaged or destroyed bombers. Unsuccessful attacks wasted ammunition and fuel. The brutal mathematics favored the Americans. 200 bombers, each mounting 12 or 13 50 caliber machine guns, provided approximately 2,400 defensive guns. Against this, German controllers had scrambled approximately 60 fighters for the intercept. The numerical disparity was approximately 40 guns per attacking fighter. German pilots compensated through superior individual skill and aggressive tactics, but skill could not overcome fundamental mathematics indefinitely. For every bomber shot down, German fighters suffered losses that could not be easily replaced. American bomber crews lost represented significant training investment, but American production capacity ensured replacement aircraft arrived faster than losses could deplete the force. By early 1944, American factories were producing heavy bombers at rates exceeding German comprehension. Boeing plants in Seattle, Wichita, and Renton produced approximately 16 B-17 bombers daily at peak production. Consolidated's Fort Worth and San Diego plants added another 18 B-24 Liberators per day. Combined production exceeded 1,000 heavy bombers monthly. Germany's entire bomber production for all types totaled approximately 600 aircraft monthly in early 1944. This included medium bombers like the Ju-88 and He-111, not heavy 4-engine strategic bombers. Germany had abandoned heavy bomber development, leaving no equivalent to the B-17 or B-24 in production or development. The industrial disparity extended beyond simple production numbers. American factories employed mass production techniques pioneered in automobile manufacturing. Standardized components, interchangeable parts, assembly line construction allowed relatively unskilled workers to build complex aircraft quickly. Quality control systems ensured reliability, without requiring master craftsmen for every component. German aircraft production relied more heavily on skilled labor and craftsmanship. This produced excellent individual aircraft, but limited production volume. Attempts to rationalize production and adopt mass production techniques founded on bureaucratic resistance, shortage of machine tools, and increasingly frequent Allied bombing raids that disrupted industrial operations. Formation is over the city, Hoffmann reported. His radar screen showed the formation spreading slightly as individual bomb groups maneuvered to their specific aim points. The lead bombardiers were activating their Norden bomb sights, feeding in altitude, airspeed, wind drift, and target coordinates. The Norden bomb sight was an analog mechanical computer of remarkable sophistication. Its gyroscopically stabilized, telescopic sight locked onto the target while the bombardier adjusted for environmental factors. Once synchronized with the target, the bomb sight calculated the precise release point accounting for bomb ballistics, ensuring maximum accuracy. In theory, the Norden could place a bomb within a 100-meter circle from altitudes exceeding 7,000 meters. In practice, atmospheric conditions, mechanical vibrations, and combat stress reduced accuracy significantly. Formation bombing further reduced precision, as individual bombardiers released on the lead aircraft rather than independently calculating solutions. But even reduced accuracy proved devastating when 200 bombers released their payloads simultaneously. 400 metric tons of high explosive and incendiary bombs fell toward Berlin in a concentrated deluge that no defensive measures could stop. The bombs required approximately 40 seconds to fall from 9,000 meters to impact. During that time, the plate formation maintained course, exposing itself to flak fire. German anti-aircraft batteries, positioned throughout the city and surrounding defensive perimeter, opened fire. The distinctive crump of 88mm flak guns echoed across the city as shells climbed toward the bomber formation. Each shell was fused to detonate at a specific altitude, creating a cloud of shrapnel that could tear through aluminum airframes. At 9,000 meters altitude, the effectiveness of flak fire dropped dramatically. The shells traveled slower in thin air. Fusing mechanisms, designed for optimal performance at lower altitudes, became less reliable. Many shells detonated too early or too late, wasting their fragmentation effect harmlessly distant from any target. The bombers flew through the flak barrage, maintaining formation discipline despite the terrifying sight of black smoke puffs appearing throughout the formation. Each puff represented an exploding shell that might have damaged or destroyed an aircraft. Crews had no way to evade or defend against flak, except maintaining formation and hoping probability favored survival. Then the bombs fell away. 200 aircraft released their payloads within seconds of each other. 800,000 pounds of high explosive and incendiary ordnance dropped toward Berlin. The formation immediately began a coordinated turn, changing course to begin the return flight to bases in England. Hoffmann tracked them as they withdrew, watching the radar returns gradually diminish as the formation moved beyond effective range. The entire raid, from initial detection to departure from radar coverage, had lasted 48 minutes. In those 48 minutes, 400 metric tons of explosives had fallen on Berlin. He removed his headphones and stepped outside the radar bunker. To the south, columns of smoke rose above the city. Even from this distance, nearly 30 kilometers from the impact zones, he could see the glow fires burning in multiple districts. The bombs had struck industrial areas, rail yards, and residential neighborhoods, with the indiscriminate destructiveness of strategic bombing. The damage assessment would take days to compile. Initial reports arriving at Doberitz indicated significant hits on the Siemensstadt electrical manufacturing complex, the Tempelhof rail marshalling yards, and scattered damage throughout residential districts. Civilian casualties would number in the hundreds, possibly thousands, once rescue workers finished searching collapsed buildings. But casualty figures and damage assessments, horrific as they were, represented only the surface impact of what Hoffmann had witnessed. The deeper significance lay in what the raid demonstrated about the balance of industrial and technological capability between Germany and its enemies. The Americans had built a bomber force capable of flying 1,500 kilometers from bases in England, fighting through German air defenses, delivering 400 metric tons of explosives from altitudes where defensive fire proved largely ineffective, then returning to base to repeat the operation the following day. This capability required industrial infrastructure operating at a scale Germany could not match. Every B-17 represented approximately 10,000 hours of labor, 500,000 rivets, and 13 tons of aluminum. The aircraft's 4 Wright Cyclone engines required precision machining of hundreds of specialized components. The Norden bomb site alone contained approximately 2,000 precision parts manufactured to tolerances measured in thousandths of inches. Multiplying these requirements across hundreds of aircraft revealed an industrial capacity that dwarfed German production. American factories built the aircraft. American training schools graduated crews at rates exceeding losses. American logistics networks delivered fuel, ammunition, and spare parts across the Atlantic, ocean to bases in England. American industrial might sustained operations that Germany's economy simply could not duplicate. The radar returns Hoffmann had tracked on his oscilloscope represented not just aircraft, but the full mobilization of American industrial society toward war production. Behind those 200 bombers stood tens of thousands of factory workers, engineers, trainers, logistics specialists, and support personnel. The entire system operated with efficiency that German planners had not anticipated when war began in 1939. German intelligence had underestimated American industrial capacity by factors approaching 10-1 in some categories. Before the war, analysts assumed American society, weakened by the Great Depression and divided by democratic politics, could not mobilize effectively for total war. This assumption proved catastrophically wrong. American aircraft production in 1944 exceeded 96,000 aircraft of all types. German production totaled approximately 39,000 aircraft. American tank production exceeded 29,000 vehicles. German production was approximately 19,000. American merchant shipping construction totaled 16 million tons. German U-boats sank approximately 3 million tons, a losing ratio that doomed any hope of severing Atlantic supply lines. Every category showed similar disparities. American factories operated 3 shifts daily, utilizing mass production techniques that German industry had not fully adopted. American workers, incentivized by high wages and patriotic appeals, maintained productivity levels that German forced labor could not match. American resources, protected by oceans from strategic bombing, remained secure, while German industry faced increasing disruption from Allied air attacks. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The strategic implications became inescapable as Hoffmann compiled his after-action report. The raid he had tracked represented standard operations for American bomber forces. Similar raids occurred daily, weather permitting, against targets throughout occupied Europe and Germany. Each raid delivered hundreds of tons of explosives. Each raid cost American forces, aircraft and crews, but losses remained within sustainable limits given production and training capacity. German defenses could inflict losses, sometimes heavy losses, but could not stop the raids. The mathematics of attrition favored the side with superior production capacity. American losses could be replaced within weeks. German fighter losses represented capabilities that could not be easily reconstituted given shrinking production capacity and diminishing pilot training quality. The Luftwaffe's decline accelerated throughout 1944. Fighter production actually increased, reaching record levels by autumn. But production increases came too late and proved insufficient given mounting losses. More critically, fuel shortages increasingly grounded aircraft that might otherwise have flown combat missions. Germany's synthetic fuel industry, always insufficient to meet total requirements, faced systematic destruction from Allied bombing. Raids, specifically targeting oil refineries and synthetic fuel plants, reduced production capacity by over 50% between spring and autumn 1944. Aircraft sat on airfields, fully fueled and armed, but immobilized by lack of aviation fuel. Pilot attrition compounded the fuel crisis. The Luftwaffe had begun the war with approximately 4,000 trained fighter pilots. By early 1944, perhaps 1,500 remained operational, the rest killed, wounded, or missing in action. Replacement pilots received abbreviated training due to fuel shortages, entering combat with skills insufficient for survival against experienced Allied pilots. The combination of pilot losses, fuel shortages, and overwhelming enemy numbers created a death spiral from which recovery proved impossible. Each successful defensive action cost resources that could not be replaced. Each failed defensive action allowed enemy bombers to destroy more industrial capacity, further reducing Germany's ability to resist. Hoffmann understood these implications intellectually, though their full emotional weight would require time to process. The raid he had tracked was not exceptional or particularly significant in isolation. It represented routine operations that would continue daily, gradually pulverizing German industry and infrastructure through systematic application of overwhelming force. The survivors from today's raid, those bombers that limped back to England, trailing smoke or flying on 3 engines, would be repaired or replaced. Their crews would rest, receive replacements for casualties, and fly again within days. The destroyed German factories, the demolished rail yards, the burned residential districts would not recover so quickly. Reconstruction required resources Germany no longer possessed in sufficient quantity. By late afternoon, preliminary damage reports reached the radar station. The Siemensstadt electrical works had suffered severe damage to 3 production halls. Output would drop by approximately 30% until repairs could be completed, assuming materials and skilled labor were available. The Tempelhof marshalling yards were blocked by bomb craters and destroyed rolling stock. Rail traffic through Berlin would be disrupted for at least 72 hours. Residential casualties totaled 437 dead, over 1,000 wounded. These numbers would climb as rescue workers continued searching collapsed buildings. Civil defense services struggled to maintain functionality under repeated raids. Fire brigades, already stretched thin from previous attacks, fought dozens of separate fires simultaneously. Medical services, overwhelmed by casualties, prioritized treatment based on available resources rather than optimal medical practice. The human cost of strategic bombing extended far beyond immediate casualties. Surviving civilians faced disrupted lives, destroyed homes, psychological trauma, and declining living conditions as infrastructure crumbled under repeated attacks. Workers arrived at factories to find their workplaces destroyed or severely damaged. Transportation networks degraded, making commutes difficult or impossible. Food distribution systems broke down as rail yards and warehouses became target priorities. German civil defense, initially efficient and well organized, gradually deteriorated under sustained pressure. Personnel suffered battle fatigue from continuous operations. Equipment wore out and could not be replaced. Supplies of medical materials, firefighting chemicals, and rescue equipment dwindled as production prioritized military requirements. By mid-1944, German urban populations lived in a state of chronic crisis. Air raid sirens sounded daily, sometimes multiple times per day. Families spent hours in shelters, emerging to find neighborhoods transformed by destruction. Children grew up knowing only war, their educations disrupted, their homes damaged or destroyed, their family members killed or missing. The psychological impact of strategic bombing remained difficult to quantify, but profoundly significant. German propaganda claimed that terror bombing strengthened civilian resolve, turning the population against the enemy through shared suffering. This narrative contained elements of truth, but obscured more complex realities. Some civilians did demonstrate remarkable resilience, continuing work despite danger and hardship. Others experienced psychological collapse, unable to function normally under sustained stress. Many simply endured, day after day, with declining hope that the war might end favorably for Germany. Military personnel like Hoffmann occupied an unusual position in this landscape of destruction. They witnessed the raids professionally, tracking formations and coordinating defenses, but they also lived in cities under attack, experiencing the same dangers as civilians. The cognitive dissonance of being both defender and victim created psychological pressures that manifested in various ways. Some personnel became fatalistic, accepting that Germany's defeat was inevitable given the balance of forces. Others doubled down on propaganda narratives, insisting that secret weapons or strategic breakthroughs would reverse the tide. Most simply focused on immediate duties, avoiding larger strategic questions that offered no comfortable answers. Hoffmann filed his after-action report and prepared for the next shift rotation. The Freya radar would continue operating continuously, sweeping the sky for the next formation of American bombers, because there would be a next formation, and another after that, for as long as American industrial capacity sustained operations. The war had entered its endgame, though official pronouncements refused to acknowledge this reality. Germany's Eastern Front collapsed under sustained Soviet offensives. The Western Front awaited the inevitable Allied invasion that would establish a second major theatre. Strategic bombing destroyed Germany's industrial capacity faster than it could be rebuilt or dispersed. The specific altitude capabilities that had shocked Hoffmann that morning, bombers operating routinely at 9,000 meters, represented just one manifestation of a broader technological and industrial superiority. American bombers flew high because they possessed engines powerful enough to operate efficiently at extreme altitude. Those engines existed because American industry had mastered metallurgy, precision manufacturing, and quality control, at scales Germany could not match. The pressurized crew compartments existed because American engineers had solved complex problems of pressure vessel design, seal integrity, and life support systems. The defensive armament existed because American factories produced 50-caliber machine guns by the tens of thousands, along with millions of rounds of ammunition. The navigation and bombing systems existed because American electronics industry had developed sophisticated analog computers and precision optical systems. Each capability built upon foundations of industrial capacity, technological sophistication, and systematic organization that Germany had failed to develop equivalently. The radar screen Hoffmann monitored displayed not just aircraft, but the aggregate result of an entire society mobilized for industrial warfare at a scale Germany could not duplicate. That evening, as Hoffmann walked through Berlin's darkened streets toward his quarters, he passed buildings with their windows blown out, facades scarred by shrapnel, walls collapsed into rubble. Civil defense workers cleared debris from streets. Medical personnel transported wounded to overwhelmed hospitals. Citizens queued for food rations, their faces showing exhaustion and resignation. This was the face of strategic bombing in 1944, not the clean abstractions of radar returns and damage assessments, but concrete human suffering compounded daily. And it would continue, day after day, because the Americans possessed both the capability and the will to sustain operations indefinitely. The raids Hoffmann tracked from his radar station represented more than tactical operations destroying specific targets. They represented industrial capacity made manifest, demonstrating through overwhelming force that Germany had fundamentally miscalculated the balance of power. The nation that had started the war with confidence in its military superiority now faced an enemy capable of delivering hundreds of tons of explosives daily from altitudes where defensive measures proved largely ineffective. The technological and industrial gap would only widen as the war progressed. American production continued increasing while German capacity declined under sustained attack. American training pipelines graduated crews faster than losses depleted units, while German training programs collapsed under fuel shortages and instructor casualties. By late 1944, the strategic situation had become mathematically insoluble from Germany's perspective. No combination of tactical excellence, defensive ingenuity, or individual heroism could overcome the fundamental disparity in industrial capacity. The war would end in German defeat. The only remaining question was how much additional destruction would occur before military and political leadership accepted the inevitable. But that evening, Hoffmann simply recorded his observations in his logbook, prepared his equipment for the next shift, and tried to sleep despite the sounds of rescue. Workers clearing rubble from the day's raid. Tomorrow would bring another formation of American bombers flying at altitudes where German defenses struggled to reach them, dropping hundreds of tons of explosives with the systematic efficiency of an industrial process. The radar screen would paint its picture of incoming aircraft. Hoffmann would track them, report their positions, watch them deliver their payload, and track them as they departed. Then he would write his report, documenting another day in the gradual destruction of Germany's capacity to wage war. This was the reality of strategic bombing in 1944. Not glorious battles or heroic victories, but systematic industrial warfare prosecuted with overwhelming material superiority. The Americans had built a military force scaled to their industrial capacity. That force now ground inexorably forward, destroying Germany's ability to resist through sheer weight of production and resources. The altitude capabilities that had shocked Hoffmann represented only one small facet of this larger industrial dominance, but they symbolized the fundamental imbalance that doomed Germany's war effort, an enemy capable of operating in regimes where German technology struggled to function, delivering destruction from heights that made defense nearly impossible, sustained by industrial production that seemed inexhaustible. These were the truths that radar operators like Klaus Hoffmann confronted daily. Electronic evidence of Germany's technological and industrial inferiority, displayed in phosphorescent green on oscilloscope screens, measured in altitude numbers that exceeded German defensive capabilities. The truth written in the sky at 9,000 meters, where American bombers flew in daylight with near impunity, demonstrating through their mere presence that Germany had lost the industrial war long before military defeat became inevitable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.